Welcome to the shape of space matrices. This lesson is on the Kronecker product. If A is an M by N matrix and B is a P by Q matrix, then the Kronecker product of A with B is the PM by QN block matrix. So we're multiplying M times P and then N times Q. And you get this very large matrix here. You're basically taking each element of A and you're multiplying it times B. So this is actually a block matrix. This entry right here is not just one element, but it's the size of B. It's P by Q, and then you have P by Q here and all the ones in between. So maybe an example will make it a little bit easier to see. We'll just take 2 by 2 matrices. But again, they don't need to be square. They can be of different sizes. So A is A, B, C, D. And B is 1, 2, 3, 4. And on the left here, I'm taking the Kronecker product of A with B. So we take A and we multiply it times B, and that's this thing in bold here. So we get A times 1, A times 2, A times 3, A times 4. Then we have B times matrix B. We get this here. Then C times this. We get this down here. And then D finally times B, and we get this. The bold is just so you can see the different inputs from A times B. Then just to emphasize, it's not commutative, or not normally commutative. If you take B times A, then you get this here. So you take 1 times all of A, and that gives you this, and then 2 times A, you get that, and so on. The one thing I want to point out is that the entries in here appear in the entries here in general. So it's basically a permutation. B Kronecker product, A Kronecker product was B, has the same entries as B Kronecker product was A, but they're permutated. And I'll talk more about that on the next slide. So this is fairly simple in concept. Where it gets complicated is when you start mixing these different matrix operations together. You'll see what I mean when we start having more than just this one operation, and then you have various combinations together, and it gets quite complex. The Kronecker product is a bilinear map. I talked about bilinear and multilinear maps in the last lesson from my linear algebra series. So here's the explanation. A Kronecker B plus C equals A Kronecker B plus A Kronecker C. So this is linearity in the second term. Then you have the same thing in the first term. And then you also have linearity in terms of scalar multiplication, is shown here. So I'm stating these without proof, and they're kind of ugly to prove. You have to have general matrices and then show how the different additions in Kronecker products equal the same thing on both sides. The second property is associativity. You can do A Kronecker B and then take the Kronecker product of that with C, or you could do B Kronecker C first and then take the Kronecker product of that with A. The Kronecker product was the zero matrix, gives you back the zero matrix, although it's larger than the zero matrix you start with, and that works with either the multiplying on the left or right. But in general, as we said on the last slide, A Kronecker B does not equal B Kronecker A. This is just one exception. And then the other thing is, and I mentioned this also on the last slide, the entries in B Kronecker A are the same as the entries in A Kronecker B. It's just that they're permutated in a different order. And you can get an equality by multiplying by what's called a permutation matrix on either side, and you can get a equality. And I'll explain what a permutation matrix is down here. In general, I mean, we can apply it to the Kronecker product, but it's generally useful. A permutation matrix is a square binary matrix, in other words, zeros and ones, that has a 1 in each row and column, and then a 0 everywhere else. So we have an example of a permutation matrix down here. Pre-multiplying an n-row matrix M by a permutation matrix P results in permutating the rows of M. Post-multiplying, or multiplying on the right, times a matrix, an n-column matrix M, permutates the columns. So here we have our permutation matrix, and here's an example matrix M. If you multiply on the left, or what I called pre-multiplying, here you notice that the first row becomes the third row, the second row becomes the first row, and the third row becomes the second row. And that's the same permutation that was done to the identity matrix to get P. Okay, so I'll leave it to you to check the details of multiplying P times N. It's pretty easy. And then M times P, you permutate the columns in the same way you permutated the columns of the identity matrix to get P here. So the first column becomes the second column, the second column becomes the third, and the third column becomes the first column. We have several more properties on this slide. The first one is called the mixed product property. And it says that if you have A Kronecker B times, this is matrix multiplication, times C Kronecker D, then that's the same as A times C Kronecker B times D. As an exercise, you may want to try proving these for just 2x2 matrices, not necessarily this one, but any of the ones we've talked about, any of the properties we've mentioned. Once we have this, then this property follows. A Kronecker B equals the identity Kronecker B times A Kronecker, the identity matrix of the appropriate size, and you can do that in either order, and you'll see how this gives you this here. Okay, so we've actually proved something given this property. Then we have some more. In terms of the inverse, the Kronecker product of matrices A and B is invertible if and only if A and B are invertible, in which case the inverse of A Kronecker B equals A inverse Kronecker B inverse. A similar property holds for what's called the Moore-Penrose pseudo-inverse, which I'm going to get to later in this lecture series, but I'll just mention it here. And it's denoted by this little plus sign here. So A Kronecker B, the Moore-Penrose of that is equal to the Moore-Penrose of A Kronecker, the Moore-Penrose of B. If you want to get ahead of things, you can look that up. It's basically where you don't have an inverse for a matrix. There's sort of another pseudo-inverse, something that's almost an inverse that you could compute for such a matrix. And this is just saying that that Moore-Penrose pseudo-inverse has this property here, which is similar to the property for regular inverses. But again, we'll get back to this in a few lessons. I have several slides on this Moore-Penrose pseudo-inverse. We have several more properties on this slide. First one is A Kronecker product was B transpose equals A transpose Kronecker product was B transpose. And if you have a complex matrix, A and B, if they're complex, then instead of transpose, you do the conjugate transpose, but you get a similar result. And if you have two matrices A and B, there's a relationship between the Kronecker product and their eigenvalues. So the lambdas are the eigenvalues of A, the mu's are the eigenvalues of B, and the eigenvalues of the Kronecker product are all possible pairwise multiples of the eigenvalues from A and B. We get this here. Then this result gives us this here, the trace of the Kronecker product equals the product of the traces. And you can see that if you recall, the trace is the sum of the eigenvalues of a square matrix A added to multiplicity. So if we took the sum of, say, the lambdas and the sum of the mu's, and we multiplied those two together, we would get all these possible combinations. So that would prove this. And then the second part is a little bit harder to prove. You need both this result and you need a result I stated in the previous lesson in linear algebra, that the determinant of A is the product of the eigenvalues. So I won't go through the details of that, but it's a useful result. The determinant of the Kronecker product is the determinant of A to the m and B, determinant of B to the n. You notice where the m is actually the size of B and n is the size of A. So it's not what you might have thought, but it's I did double check this. Then there's the Kronecker sum and exponentiation. I haven't seen this used a lot, but I'll state it here for completeness. So the Kronecker sum of A with B is A Kronecker product with the identity matrix, and then plus the identity matrix Kronecker product with B. And again, you notice the strange mixing here. It's A Kronecker product with I of size m, where m is actually the size of matrix B, and then n is the size of A. And again, I double checked this, and it's not what you might have thought, but it works this way. Then if you take the exponent of the Kronecker sum of A with B, it's actually the exponent of A Kronecker product with the exponent of B. Okay, so that's it for this lecture. I know there's quite a bit of identities. I'll try to remind you when I use these later on. I know it's a lot to absorb. And I have 4 more lectures in this series, and they're kind of similar to this, where there's a lot of properties for different matrix and vector functions. And I prove just a few. A lot of them I just state. And in some cases, I also have examples to illustrate the point.